Another equation that we can derive from the kinematic equations with special conditions is the range equation. And typically, if we wanted to find how far something travels, like let's say we have this volcano here, and let's say there's a projectile launched out of it at a magnitude, a velocity of 25 meters per second at an angle of 35 degrees above the horizontal, or measured at standard position, and it launches over here, and then it lands at a point 20 meters below from where it was launched. So this would be a delta y based on our coordinate system here is equal to negative 20 meters. So we can use the kinematic equations, and we can first evaluate the y direction for the time in the air, and we can say that delta y is equal to v naught yt plus 1/2 ay times our time squared. Given that we have a delta y, we know that v naught y is v naught sine of theta, and we know acceleration in y is negative g. This becomes a quadratic in t. And so then we can solve this for t via we can factoring, completing a square, or probably just the quadratic formula. So we'd solve this for t using the quadratic. A quadratic method, or a method for solving quadratics. And then from there, when we'd use basically the same form, but in the x direction, we would use delta x is equal to v naught xt plus 1/2, and we know that it's projectile, so acceleration x is 0 times the time squared. So solve this t and just multiply it by its horizontal component of velocity. So we can solve a problem like this with our kinematic equations. But let's say that we have a different scenario. Let's say that we have a delta y which is equal to 0. So let's say that we have a projectile which is launched. Here's the ground, and it's launched at some initial velocity, v naught, at some initial angle, theta, and then it lands at the same height from which it was launched, such that delta y is equal to 0. Then we have this equation above, this delta y equals v naught yt plus 1/2 ay times time squared. This simplifies down and becomes 0 is equal to, and we know that v naught y is going to be v naught sine of theta, as long as theta is given in standard position, and then times time plus 1/2, and if we're on Earth, we have acceleration in y on Earth using a traditional coordinate system, like the one that we had with the volcano previously. Here's our x, here's our y. So the acceleration y would be negative g, and then times time squared. And then if we factor this out, we have 0 is equal to t times v naught sine theta minus 1/2 gt is what this comes down to. So we solve this, and we see that we have 2 times. We'll have time equal to 0, or time is going to be equal to, we have 2 v naught sine theta over g. Solving time equal to 0, time equals 2 v naught sine theta over g. So these are the 2 times at which delta y equals 0, which makes sense that one of them is time equal to 0, because clearly, delta y was 0 before it was thrown. And also, this is the other time over here. So if we're interested in how far it actually goes, this delta x, if I want this delta x right here, then I'm interested in this later time. Obviously, this one is not very interesting to deal with. So let's use that time and plug this into our delta x equation. So then how far does it actually go? Delta x equals v naught xt plus 1/2 ax times the time squared. Again, assuming projectile motion, this acceleration is 0. So then we have delta x equals v naught x would be v naught cosine theta, and then times the time we're interested in is this 2 v naught sine theta over g. So times 2 v naught sine theta over g. And so then this becomes our delta x here is equal to, this will be v naught squared times 2 sine theta cosine theta all over g. But this is a trig identity. 2 sine theta cosine theta is the sine of 2 theta. And so then delta x becomes v naught squared times the sine of 2 theta over g. This is what we call the range. And this is the range equation. So this is the range, or sometimes we just say R. So it's the magnitude of the velocity squared times the sine of twice the angle in standard position divided by g. And this is how far something travels. And so, and this is how far something travels only if it lands at the same height from which it was launched. Remember that we had to have delta y equals 0 in order for this to be true. If delta y is not equal to 0, we need to go back up here, and most likely we're going to have to solve a quadratic to get our time first. So this is only if delta y is equal to 0. So some interesting things about this. We see here, this is the sine of 2 theta. And so then the way we maximize the range would be to get our sine function a maximum value. So we know the sine of 90 is the greatest value we can possibly have, right? So this is our sine of 90 is equal to 1. So this must mean that 2 theta is equal to 1. So, I'm sorry, 2 theta is equal to 90. So then theta must be 45 degrees. So the farthest we can launch something is at an angle of 45 degrees. And this, of course, is still assuming projectile motion, so no wind resistance, etc. But it makes sense. If we launch it too high, then it'll go, or if we launch it, at like 89 degrees or 90 degrees, it'll go straight up and it won't go over at all. If we launch it at 0 degrees, it'll just hit the ground as soon as we launch it. So somewhere in between, it makes sense that that would be our maximum range we can get. And so this is shown from this range equation here. Just kind of showing some pictures of this. We have some calculations for the range equation based on different velocities. You can plug these in, but if you have a 30 meters per second at an angle, all of these are at 45 degrees. This is our maximum range here. Then the range is 30 squared divided by g, right? We just have 30 squared times the sine of 2 theta, since theta is 45 degrees, this is the sine of 90. So we have 30 squared divided by 9.8 is 91.8. Similarly, at 40 meters per second, this is 40 squared divided by 9.8. This is 50 squared divided by 9.8. And with different angles and all the same velocity, we can also show all of these at 15 degrees, this distance here with 128 meters, this is going to be 50 squared times the sine of twice the angle, so this times the sine of 30 divided by 9.8 g, and that's the 128 meters. So, which actually is the same as 75 degrees and 15 degrees are the same, and it can be shown here. I won't go through the proof here, but it can be shown that if they are equal distance from 45, then they will actually have the same delta x. So if you're 40 degrees and 50 degrees would actually have the same range. 10 degrees and 80 degrees would have the same range as well. And so two angles which are equidistant, their angle measure is equidistant from 45 degrees, will have the same range. It's a fun little fact there. So there's a range equation and some of the results of it.